the recording, okay?
Start हो गया.
Welcome back to the lecture 19 on Riemannian symmetric space. I really feel very embarrassed from within that I could not take the two lectures, even though there was some reason for that. And hope today there will be no problem. So actually recall in the last lecture I have really proved this something like this GKRN. This GKRN is the real Grassmannians of K-planes in Rn. GKRN is B is a collection of all B, so that B is a k-dimensional subspace of Rn. Okay, so we have proved that both group SON and ON act transitively on GKRN, and using this so-called orbit stabilizer relation, we have got that GKRN is can be identified with ON mod OK cross ON minus K. Similarly, GKRN can be identified with SON mod S of OK cross ON minus K. So this side, this thing, right hand side, this is a really smooth manifold, and using that this identification, we are able to give a smooth structure on GKRN. So and that GKRN is a compact connected smooth manifold, and this GKRN is diffeomorphic to Gn minus KRN. Similarly, G1 of Rn is nothing but real projective space of dimension n minus 1, and dimension of GKRN is equal to k into n minus k. Okay. So now today we will really discuss something about GKCN. This GKCN is really this is for complex Grassmannians of K-planes in C. So this is really here also I will take one less than K less than n. So definition is exactly similar to the GKRN case. So, GKCN is really sorry. This is a collection of all V, so that V is a k-dimensional subspace of V, like subspace of CN, right? Sorry. Like the GKRN case, here actually two groups will act naturally on GKCN. So both UN and SUN will act transitively on GKCN. And you can, using exactly the similar argument, you can prove exactly similar argument to that of GKRN. So one can show that this GKCN can be identified with UN mod UK cross U of n minus k, and same thing is can be identified with SUN mod S of UK cross UN minus k. Now this thing, as I have said, that this has a smooth manifold structure, so we can borrow that smooth manifold structure to GKCN with this identification. And since this UN and SUN both are compact and connected, so you will get that GKCN is a compact and connected smooth manifold. Okay, so let me write that observation. So first observation is really GKCN is a compact and connected smooth manifold. Now there is a symmetry in between k and n minus k. So GK, therefore GKCN is really will be diffeomorphic to Gn minus KCN. So this is a diffeomorphism. And this is really third thing is G1CN. G1CN is really CPN minus 1. It's really complex projective space of. Okay, so this is really a complex dimensional model. This is not the real dimension. This is the complete dimension. This is the thing, and similarly, you can really calculate the dimension of this GKCN. Okay. Now we have another thing that GKHN. This GKHN, this is really quaternionic, Grassmannian of K-planes in HN. This, and here also you assume that 1 less than equal to K less than N. And this has a similar definition. This H actually is a set of all quaternions. So GKHN is the collection of all sub B, so that he is a K-dimensional subspace of H. Okay, so here actually SPN analog of UN is really SPN. So SPN you will act transitively on GKHN, and using exactly similar argument you can show that you also get and that GKHN is really can be identified with SPN. It's mod SPK cross SPN minus K. So you know that in case of a real thing, we have two groups ON and SON, right? And similarly, in case of complex thing, you have two groups UN and SUN. But I have explained you that in case of quaternionic matrices, we have to give a new notion of determinant, and there will be only one group, only SPN. Any matrix belonging to SPN has to be is of determinant of 1. So there, in this case, you will get only one representation. Okay, now also we have shown that SPN is connected and compact. So therefore, we have the following observation. First observation. GK chain is really compact and connected smoothly. The second thing is GKHN is really diffeomorphic to Gn minus K. So this is the diffeomorphic. Third thing is G1HN is equal to, this is written as HPN minus 1, and this is called quaternionic projective space of dimension n minus 1, but that is always quaternionic dimension. Quaternionic dimension n minus 1. Nobody says quaternionic dimension. Okay, I am just really writing this thing because we will not. So for clarification, I am just writing. So today we will really prove that GK Rn, all these Grassmannian manifolds are really Riemannian symmetric space. But for that, we have to really give some differential geometry preliminaries. Okay, so for that, I recall a very proposition which I have wrote it to you in this thing, in that attachment actually. I have posted this thing. Proposition is, suppose let n subset of n be an embedded manifold, embedded submanifold of n. Suppose f from m to n, suppose f from m to m is smooth, and f of n is really contained inside n. Then f from n to n is smooth. So it is say that if n is a embedded submanifold of n, then restriction of a under this condition f n subset of n, the restriction of f from n to n is smooth. This is only true for embedded submanifold. Okay? This is not true for immersed submanifold. So for proof, you can see that you can see John M. Lee or Kumration or algorithm. Or algorithm, you can see. So this is a sort of standard result. In fact, we have used this result. One application actually we have used many times this result, but I didn't tell you. Suppose let A is a orthogonal matrix. So you know that A from A will map from Sn minus 1 to Sn minus 1. Okay. So how do you conclude that A from Sn minus 1 to Sn minus is smooth? And one really concludes that from using this above proposition. Okay. So let me write that thing. Just so let A belongs to N, and then the A will A from Rn to Rn is smooth because Rn has a global chart and A is a linear map, so A is from Rn to Rn smooth. As so Sn minus 1 is an embedded submanifold. Submanifold of Rn, and A of Sn minus 1 is contained inside Sn minus 1, and AF contained inside Sn minus 1 by previous proposition. A from Rn to Rn is smooth. So this is a very important proposition. We will use this
Sn minus 1 to Sn minus 1.
Oh, yeah, thanks. Sn minus 1 to Sn minus 1. This is an important proposition. We will use this. Similarly, there are also important theorems. For so let n subset of M be a smooth submanifold of M. Here actually I assume that this is a only submanifold, not necessarily embedded. Suppose F from M to S be a smooth map, then F from N to S is smooth. Okay. If you restrict that map in the domain side, then F is smooth. Now similarly, suppose F from S to N be a smooth map so that F has subset of N, then F from S to N is smooth whenever F from S to N is continuous. So in the range side, if you restrict the map, okay, then it is not necessarily smooth. You have to assume that F from S to N is continuous. Okay. So one thing is if this is an embedded submanifold, so this condition F from S to N is continuous will come from this fact that F S to M is smooth, because If something is an embedded submanifold of n, then that has actually subspace topology of n. So therefore, this will come automatic, and therefore will have two corollary. So corollary, let n subset of M be an embedded submanifold of n. Suppose f from S to M will be a smooth map, so that fs is subset of n. Then f from S to n is smooth. Okay. So none means restriction in the range side is also smooth. Okay. And the last thing is the proposition which I have just wrote in the beginning. Suppose f from M to M is smooth map, so that fn is subset of n. Then f from M to M is smooth. For the time being, this proposition which I wrote in the beginning, this is actually is going to important, and you have to really just now remember this thing. Okay. Now, and these are also important things. It will come in different occasion, come on different. Also, I have given a definition of a smooth continuous group action. So let that means just a group for acts on a topological space in a continuous way. So this is a definition. Let G be a locally compared Hausdorff topological group and M be a Hausdorff topological space. The continuous group action of G on M is a continuous map which takes G comma M to the point G dot M from G cross M to M, so that this M going to G dot M is a homomorphism of M for each G belongs to G. And second thing is just the condition of group action. G dot H dot M is equal to G H dot M for all G comma H belongs to G and M belongs to M. The topological space M above is called a G space, okay, and the group G is called a topological transformation group. Okay. This is probably you have seen this definition, I think. So if you replace this so-called topological group by Lie group and topological space by smooth manifold, and wherever continuity is there, you replace by this smooth map, then you will get a smooth group action. And this is the definition. Let G be a Lie group and M be a smooth manifold. A smooth group action of G on M is a smooth map from G cross M to M, which takes this point G comma M to G dot M, so that M going to G dot M is a diffeomorphism of M for each G belongs to G, and G dot H dot M is equal to GH dot M for all G comma H belongs to G and M belongs to M. So this wherever continuity is there, I have replaced by smoothness. Okay, and the group G is above called Lie transformation group of the G space M. Okay. So now, okay, okay, suppose G acts on M smoothly. Then I'll take P belongs to N, and I look at the orbit of P under the action of G. So that is G dot P, and this is by orbit stabilization. This is G mod GP, where GP is the really uh, stabilizer of P in G. G belongs to G, so that G dot P is equal to P. Last time I told you that this GP is a closed subgroup of G. Last time I told that G mod GP is a smooth. This is a smooth manifold. Okay. Now, if this is a smooth manifold, then you can borrow the smooth structure to G dot P. So G dot P is actually a smooth manifold. Now the theorem says that G dot P is really uh, okay. So G dot P is a smooth manifold, and by definition, since you are borrowing the smooth structure from G mod GP to G dot P, therefore G dot P is diffeomorphic to G mod GP by definition, because you are borrowing the smooth structure from G mod GP. The theorem says that G dot P is a submanifold of M. G dot P is a subset of M. So this is really submanifold of M. The theorem says. And if G is compact, if G is compact or G mod GP is compact, then this is an embedded submanifold. G is compact, then G dot P is an embedded submanifold. Okay. So
So how this compactness is helping to be it embedded submanifold?
Compactness, because you, for embedded submanifold, you want the image to be homomorphism, right? But if you
Basically,
have,
the topology should be the subspace topology, right? For
yeah,
being
yeah.
the embedded
The thing is,
submanifold.
you have a theorem like that. If x from x to y, if x is compact, okay, and this y is Hausdorff,
Then it's homeomorphism.
one-sided is thing continuity will give you homeomorphism. For that
Mhm.
reason, this compactness is really a
Okay.
sufficient condition. Okay. So I have really written that theorem in a realized way. This theorem is let GBLE transformation group of
This
a,
will happen in case of Grassmannian, right? Because Grassmannian is
yes,
compact.
yes. But the thing is, Grassmannian, do you have an ambient space M here? Do you understand what I'm saying? Question? Did you get my question? You
No,
will see that.
Grassmannian you are seeing as like ON mod ON
Okay,
cross, sorry, OK cross ON minus K, right?
okay, so let us see. The Grassmannian GKRN is really OK cross, sorry, ON mod OK cross ON minus K, right? This was the thing. Now we are just borrowing the smooth structure to GKRN. Okay, there is no really embedded. Okay, so you will see this thing actually. Okay, you are just, there is what is the aim here actually in this case. G you can really get ON. What is the aim here? So you do not get any M here, but we will get an M. That's actually, that is very. You will see this question later. Okay. So this is the thing. So let G be a Lie transformation group of a manifold M. That is G acts smoothly on M. Then for each P belongs to M, the orbit G dot P is a submanifold of M diffeomorphic to G mod GP, where GP is something like the stabilizer of P in G. Moreover, if G mod GP is compact or G is compact, then G dot P is an embedded submanifold of M. Okay. So this is the theorem, so which I have explained you. So now, okay. So now discussion. So we are moving towards that our goal that to show that GKRN is a Riemannian manifold, but we have to prepare something discussion. Let be this be a real inner product. This be a real inner product. Okay. So if that is the real inner product space, then you can really be identify with Rn if you fix an base orthonormal basis. This implies B has a smooth manifold structure and diffeomorphic to Rn. It has a smooth manifold structure, and it is, and so now if let P belongs to B, then you can identify that TPV with P. Okay. Now so you can really give a Riemannian metric on this B. Okay, so let UV belongs to TPV. So this you can define this GPUV is equal to this inner product U and V. This association P going to GP is really a Riemannian metric on V. So that means you will get that this B, this thing. You call that VG. So this is the metric G, where GP is defined like this. So GGP is a Riemannian manifold. And is isomorphic to this. It is clear that it will be isometric to this Euclidean thing, Rn and GRn. So okay. So that conclusion is any real inner product space is a Riemannian manifold in a natural way. and that it is asymmetric to the usually Euclidean space. Okay. The second thing is
Why it is isometric to the Euclidean metric?
you can is it
Maybe obvious, I don't know.
think little bit. I am not able to. Okay, so
Because there can be other metrics also, right? Or they are equivalent.
no,
I
you,
don't-
you sort of you are really fixing this. This is actually what you are sort of fixing this inner product. Okay.
So then you
So
should say that this is the Euclidean inner product.
no, that is not the inner product. You are if you really fix a inner product. Okay. Uh, then you just fix a basis with respect to this. Suppose x1, sorry, so v1, v2, vn, okay, of v.
Yes.
Okay, so you will get a coordinate chart. Okay? So if v is really something like alpha 1,
Yes, I understand.
okay, so coordinate chart, and in both in this case actually if you get some coordinate chart like u1, u2, un, in both the cases, actually, this matrix is really du1 square plus du2 square plus dun square. So for that, it will be actually isometric to Rn, grn. Or you can do an explicit. You can actually take it an exercise. Okay. Okay.
No,
Will I?
I'm slightly confused because you take hyperbolic space, okay?
Yeah.
That is diffeomorphic to Rn. You want agree, right?
Hyperbolic spaces. Okay.
So they're diffeomorphic,
Yeah.
and the hyperbolic space has a single chart, right? If you take the like, let's say 2 dimension, you take the hyperbolic plane, that
Hmm.
model.
Hmm.
It's basically R2, right? But they have a
Yeah.
different metric.
Diffeomorphic to R2. Okay. That's okay.
But they have a different metric.
But that is not an inner product space, right?
Okay, you are taking inner product space
So
itself.
this sort of this is sort of a really this metric I am not really changing. Also, this is a so every point p I am giving the same constant this inner product. That
Okay.
is the key actually.
Okay. It may be obvious. I'm missing something. It's okay. You please carry on. Sorry.
No, actually I can do it, but actually okay. So I will do next lecture. I will clarify this thing.
Yeah, sure.
So
No problem. You carry on.
this is it was just okay. So this is. So let B is really you take this MNC. Okay, so you can. So the question is really can you give an inner product in MNC? So if I will ask the question to all of you, then you will say the question is really can you give an inner product on MNC? You will say that you write A in this form Aij and B is really Bij, and I have to give an inner product on this space AB. You will say that this is really Aij, Bij bar. Ij is equal to 1 from 1 to n. And this thing actually you are looking A as an element of Cn square and B is an element of Cn square. You are sort of giving that inner product. Then you can write that thing in a compact form. This is test of Bist array. Okay, so this is called really Hilbert-Smith inner product. So this is the more natural inner product for the space of complex matrices. So this is called Hilbert inner product. Okay, so this is really the thing, and now the thing is let B be a B subset of MNC be a real vector space closed under conjugate transpose. I'm not assuming that B is subset of M and R. I'm just saying B subset of MNC, which is real closed under conjugate transpose. So, sorry. So one can equip B with this so-called Hilbert-Smith inner product because it is subspace and it's closed under inner product. Okay. Now the thing is, okay. So therefore, by previous discussion, so previous discussion, this A. So this is a B is a Riemannian manifold. So in a very in a canonical way. Okay. So this is the thing we really understand. Now our goal is to really show that GKRN is really GKRN and GKHN, GKCN and GKHN. These are all Riemannian symmetric space. First, we know that these are smooth manifolds. First, we have to show that these are really Riemannian manifolds, and then actually we have to really show that these are Riemannian symmetric space. So first, I will pick this thing first. GKRN real real Grassmannian. So goal is to show. First thing is really GKRN is a Riemannian manifold. And second thing is I have to show that GKRN is really is an RSS, Riemannian symmetric. Now understand this very carefully. Suppose I am able to show, that GKRN is subset of some MG, where this MC is a Riemannian manifold. So this is really, and if I can show somehow, and I am able to show that GKRN is a submanifold of M. So if you restrict this rest metric of M to GKRN, that will be a Riemannian metric on GKRN. Okay, so that will show that this is really GKRN will be a Riemannian manifold. Okay, so what we will show? We will show that GKRN really is a subset of some B, where B is a really
Here you are
real.
talking about embedded submanifold.
No, so if something is a submanifold of a Riemannian manifold, then that is a Riemannian manifold, whether irrespective of this fact that is really embedded or immersed. That doesn't really matter. Okay, but in
how
this
do you
case,
get that smoothness of the metric, etc.?
smoothness you will get there. There is no problem.
Because you will
So,
be restricting the metric to this submanifold, right?
so there will be nothing problem actually. You have to,
Okay.
actually I told you that in that thing. Okay, so you will not really get. You can just look at what I will. Okay, so what is the metric? Okay, so actually, okay, so suppose n is a submanifold of Mg. Suppose this is the thing. So I want to define some G of n, and I have explained that Gn n can be if n is a submanifold. then you can really think that n subset of n, and TPn is really subset of TPn. Okay. So Gn of u, okay, so G, so I have to so I have to define any Riemannian metric on n. So Gn of simply uv is equal to this is the, okay, let us call this G tilde. So G tilde n u, G of n u. So G is the metric on n. So you do not really need here actually anything like embedded or something like that. So this is the Riemannian metric on n. Okay, so these are very simple things actually. Okay. So what I am saying that I will show that GKRN is a subset of some V, where V is a real subspace of a set of all complex matrices, and that is also closed under this conjugate transpose. So we have seen that this V is a Riemannian manifold, and since GKRN will be submanifold of V, then that will give a Riemannian metric on GKRN. We have sort of this idea actually we have used in various cases, like suppose Sn minus 1 is a submanifold of Rn. We have restricted the metric of Rn to Sn minus 1. Then we get that Sn minus 1 is a Riemannian manifold. Okay, so this is the simplest thing. So we have to really, this concept is very important. Okay, let us erase that thing. Okay, so we are doing that part. So what I'm saying, oh, okay. So first important proposition. Proposition, let P belongs to MNR be an orthogonal projection. So what does that mean? That means that is really A is equal to, sorry, P is equal to P transpose. So let us write P is equal to P transpose and P square is equal to P. This means simply that. So then there exists an orthonormal basis. So let us really assume that orthogonal. Just wait, I will drink some water. And dimension of image of P is equal to K. So then there exists an orthonormal, what is spelling? Orthonormal basis B. See, this is really V1, V2, Vk, and this Vk plus 1 and Vn. So that if you look at the matrix representation of P with respect to this B, then that will be something like I k cross K and 0, 0, 0. And this is, what is this PB? PB is the matrix representation of P. P with respect to. Okay, and how to do that? This is very simple. If you choose this thing like this V1, V2, Vk, this belongs to image of P, orthonormal basis, and these other things you take that belongs to image of P per, then you will get that. Okay, you will see that matrix representation P with respect to B will be I k cross K and 0, 0, because dimension of image of P is equal to K, I have assumed. Okay, so equivalently, so equivalently, there exists a matrix A belongs to ON, so that This A transpose PA is equal to really I k cross k 0 0. This is also clear because this is the same statement I am really writing in a different form. For instance, one can take here. For instance, one can take this A is equal to really simply that V1, V2, Vk, and this Vk plus 1 and this Vn. So this is really you can do. Now from here actually trace of P is really trace of A transpose PA, and this is really K, and this is K is I have really dimension of image of P. So this you get that for a orthogonal projection, trace of P is equal to dimension of image of P. This is a very thing. Now second important fact, we will use this thing. So let V be a k-dimensional subspace of V, subspace of Rn, subspace of Rn, and let PV be the orthogonal projection onto V. This is the orthogonal projection onto V. So let A belongs to N. Then A dot A applied on PA, and let P of AB be the orthogonal projection onto AB. So AB is also a k-dimensional subspace because I am taking it to N. Then claim. Then we have this following claim. This claim is really P of AB is equal to really A PV A transpose. And this is the thing, and proof is very simple. First, observe that this AB PV A transpose is really an orthogonal projection. That is really A PV A transpose is really A transpose is A, and A PV transpose, this is A transpose. But PV transpose is equal to PV. So this is the thing. Now A PV A transpose square, and that is really A PV A transpose and A PV A transpose. Now use this fact that A transpose is identity. So this will get you really A PV square A transpose, and PV square is equal to PV. So this is A PV A transpose. Now since this is orthogonal projection, and so dimension of image of A PV A transpose is equal to really trace of A PV A transpose, and this is equal to trace of PV because this is K. So A PV A transpose is an orthogonal projection onto a k-dimensional subspace of Rn. But the thing is, Rn AB is a k-dimensional subspace. So let W is equal to really AB, where V belongs to B. Now A PV A transpose W, and this is A PV A transpose. A W you can replace by AB, and this is really A PV A transpose A identity, and A PV of B is equal to B because B belongs to B. and PV is the orthogonal projection onto V, and AB is called W. So this means this AB is really is in the image of this APV transpose. So this implies that APV transpose is orthogonal projection onto AB. Thus, P of AB is really APV transpose. So this is clear. Now I have this thing. So GK. Okay. So I have this thing GK. Let us define. Let WK. I define a subspace. This is really Q belongs to MNR. So that Q is equal to really Q transpose, and Q square is equal to Q, and trace of Q is equal to K. Q is equal to K. So I have a very, I get this GKRN, and I get these two spaces WK. You take this V in GKRN and you can associate to this PV. This PV is the projection onto V. This is the projection onto V. And this B is really belong to an element of WK. Similarly, if I take an element Q here, okay, so if you take Q here, this I can associate an element from GKRN that is image of Q. So, and this is a really one-to-one correspondence. So there is a one-to-one correspondence between this GKRN and WK. So I can identify this GKRN and WK by this map. So GKRN is identified with WK. Now if you look at the description of WK, so there is a very natural vector space where V, okay, where this WK is a subspace of that WK. So what is that natural vector space? This is really this set sits inside the set of symmetric matrices. WK sits inside symmetric matrix. SN, okay, where SN is really, this is really what? This is really Q belongs to MNR. Okay, let us write X. X belongs to MNR. So that X is equal to X transpose. We have used this notation in the beginning. So this is the thing. And this is equipped with the inner product, and this is really, there is an inner product here. This is the inner product. This is a trace of XY. This is exactly the Hilbert-Schmidt inner product. Because this is a real matrix, so A star will be A transpose, and this SN is closed under SN is really set. This is really the restriction of Hilbert's minimum. So that means SN is a really Riemannian manifold. Yeah. So this SN is a Riemannian manifold. So SN is a Riemannian manifold. Now we have this situation. So GKRN, this is identified with WK, and this is really SN, and this is a Riemannian manifold. This is a Riemannian manifold.
So Muna, this SN now,
Sorry,
what you
SN.
have described earlier, so this will have Euclidean inner product.
Not Euclidean inner product.
Because again, here also you are defined for every point, right? SN, you are defining the inner product like
This
considering
is
at each. Not, see, you are taking in two vectors, let's say x and y, and you're defining the inner product, right?
Hmm.
So Sn,
Yeah,
it's
tell
not
me.
for all point is the same inner product, right?
Now this is a vector space also.
Hmm. So this is a
Sn
vector
is a
space and
vector
this is the
space,
inner product.
inner
Yes.
product. Now all, for
Hmm.
the all point P that
Hmm.
I have described, that this is the same thing actually. So let me go back to that. I have discussed.
Maybe I am missing something.
So B is a real inner product space, right?
Yeah.
B is a subset of Rn. The B has a smooth manifold structure. Okay. B is not subset of. B is really can be identified with Rn by this orthonormal basis if you fix. Therefore, B has a smooth manifold structure. If you do you agree this point?
Yeah. Any n-dimensional real vector space is isomorphic to Rn. So it's a vector. So then it's
Yeah.
the same structure you can borrow, right?
If you let P belongs to V, TPV is equal to V.
Hmm.
This UV, TPV, GP of UV is equal to this UV, inner product of U and V.
Yes.
This is the Riemannian metric on V.
Yeah.
So that means any, my point is any vector space, real inner product space is a Riemannian manifold in this way.
Hmm.
In this way, Riemannian manifold, but I am in that case actually I am getting that WK is a subset of Sn. Okay, so there is a inner product on this Sn. Okay, this is a
Yes.
Hilbert-Smith inner product. So Sn is
Hmm.
a inner product space. Okay, I am not specifying the Riemannian matrix now because I have
Okay.
specified that in that thing. I am just
Hmm.
only saying that this is a Riemannian manifold. Is it clear?
You are saying Riemannian manifold with respect to this metric, right?
This is not the metric. You have to give the metric at every point, right?
Yeah.
This
Okay, you
is
are
not
going
the
to give
metric.
the metric. You are going to give the metric now.
No, I am not going to do the metric. What will be the definition of metric? This is the metric.
See,
For each point,
for this description, V is a real inner product space. So Sn is also a real inner product space, right?
yes, yes.
And in the same way, like this, Sn will be a Riemannian manifold. That's what I'm
Yeah,
saying.
in the same way.
Are you
But
using that?
yes,
Okay.
this is the effect you are using. Is this clear, Kapendu?
Yes, Munala.
Yeah. So if
Riju, Riju?
you have given metric here, if you give
Yes, Munala. Yes.
Yes. So GKRN is WK subset of SN. This is this are not, you should not treat this as a metric. This is metric will come from this inner product, but this is just inner product. Okay. So GKRN subset of WK subset of SN. Okay. So that means with this identification, I can really say that GKRN is a subset of SN. Okay. So the problem is, so with this so okay, let us see via this the identification, via this identification, GKRN is a subset of WK. I can say. So there, understand this very, listen to this very carefully. GKRN is a subset of SN by this identification. But you do not really know this GKRN has a manifold structure, okay? Has a smooth manifold structure. That's okay. And SN is a Riemannian manifold. It has own its manifold structure, but we are not sure that whether this GKRN is a submanifold or not. It is a smooth manifold. SN is a smooth manifold, and GKRN has a smooth manifold structure. We are not sure that whether this GKRN is a submanifold of Sn or not. This is a problem. Okay, so we have to first prove that thing. Okay, then actually if you can show that GKRN is a submanifold of Sn, then by I have explained you that you can immediately conclude that GKRN is a Riemannian manifold. So this is the problem. So GKRN, but it is not, but we are not clear. So that is not clear. I am just writing this thing, but these are only clear whether GKRN is a submanifold of Sn or not. The subset of whether GKRN is a subset of Sn or not. Or not. Sorry, GKRN is a submanifold of Sn. Of Sn. So we have to really sort out that point first. So what we will do, we will give a smooth manifold structure on WK. We will just identify WK with GKRN, and we will give a smooth manifold structure on WK. Okay. So and and we will see that smooth manifold structure on WK is coming from GKRN. So what I am saying this something like this. So let me clear this very clearly. So what I am saying that we will just identify GKRN with WK set theoretically. Only set theoretically we will identify GKRN and WK. Okay. Then on WK we will give a smooth structure so that WK becomes a smooth submanifold of Sn. Okay. And later I will show that this smooth structure on WK is really coming from GKRN. Okay. So let me say this once more. What I am saying that we will just identify GKRN with WK, and we will give a smooth structure on WK. Okay. So that WK becomes a submanifold, embedded submanifold of Sn, and we will show that smooth structure on WK is coming from GKRN. Okay. So for the time being, we are not equipping this WK with any smooth structure of any smooth structure. Okay. So is this clear, Pritam?
Yes, Munadar.
Okay. So this is the thing. Now we have to use that theorem. So let us read. This GKRN, we have this identification. GKRN and WK. Okay. So on GKRN, ON acts on GKRN, right? Okay. So I now want to lift that action to WK. So you really take this here B belongs to GKRN. You apply it to this under this identification B going to P dot B. Now let A belongs to ON. So you take this A dot B here. Okay. So A dot B. So A belongs to ON. So A dot B will go to P of A dot B. And P of A dot P is really P of AB. And this is really A. We have proved that A, PB, A transpose. So we are able to define an action on WK. So ON has an action on WK defined by A dot Q. Okay, this is really A Q A transpose. Okay, so A belongs to ON, and this is really Q belongs to WK. Okay. So let me write that action. A dot P is really A dot Q is equal to A Q A transpose. A belongs to ON and Q belongs to W. So this is clear actually. One can check that. So check that this defines action. you can say an action of. Now let Q0 is equal to your ik cross k and 0 0. Okay. And this is really that Q0 this is, and clearly this Q0 is the orthogonal projection is the orthogonal projection onto orthogonal projection onto this E0, where E0 is equal to span of this so-called E1, E2, E3. So, okay, since this is the same action, actually I'm seeing in a different way. So as we have seen that as ON acts transitively on GKRN, so this implies ON will also act transitively on this on WK. Okay, so this is really it is clear from this thing, but transitiveness is also clear from the proposition which I have really stated you in the beginning. This thing, if you really look at this thing, so there exists a O belong. This is the proposition. If P is a orthogonal projection, so that dimension of image of P is equal to K, then there exists always A belongs to ON, so that A transpose PA is equal to this thing, and this is really your Q naught. Okay, this is really your Q naught. So this is really Q naught. So transitiveness is also clear from the previous proposition. So, ON acts transitively on where WK is also clear from previous proposition. So this is the thing. Now, okay. Now we have this identification GKRN with WK. So GKRN is really, if you look at this thing E0, and this is E0 is mapped to Q0. Okay. If you look at the stabilizer of ON inside E0, and we expect that this stabilizers, all the things are same, indeed they are same. So in this case, actually what is really the stabilizer of ON inside E is not, this is really OK cross ON minus K. Okay, so in this case, it will be also ON can OK cross ON minus K, because this is the same action, but you can really prove directly this thing. So let us do that for our clarification or for our clarity. So A is equal to say B, C, D, E. This belongs to really stabilizer of ON, stabilizer of Q naught inside ON. That is the same thing as this implies what? A Q naught, A transpose is really Q naught, and A Q naught is equal to Q naught A. And this Q naught is really, okay, so A, you can write that B, C, D, E. So you really partition this B, C, D in such a way that B belongs to M, K cross K. Okay, so you will see that what is the dimension of this. So this is IK cross K and 0, 0. It's really I0, 0, 0. This is K cross K matrix into this B, C, D. So this is almost like elementary row matrix multiplication, and you have to really take this B belongs to MK R, C belongs to M K cross N minus K R, and B belongs to really M n minus K cross K R, and really E belongs to M n minus K n minus K. So this is the thing you have to take. So if you, this is almost like a matrix multiplication, so elementary rule matrix multiplication. So this is BD and 0 0. This is really BC and 0 0. So you will get what? D is equal to 0 and C is equal to 0. So D, this non-diagonal parts are will be 0. So hence this, hence A is of the power. This is really B 0 0 E. Now as A belongs to ON, so this implies B belongs to OK and E belongs to really ON minus 1. This is the same thing. Hence we get a stabilizer of ON inside Q naught. Really, this is the same content inside OK. And conversely, it is easy to see that. See that this OK cross ON minus K is contains a stabilizer of ON inside Q naught. Now, hence, this is a very this is the expected thing. OK cross ON minus K. Now, so thus this ON acts on WK transitively, and this is the stabilizer. Now so we extend this action of we extend the action of ON on WK to SN. On WK to SN. Okay. So if that is the case, then and what is the action? And the action is given by this thing. It is given by this. So you take A dot X. Really, this is same action. AX A transpose, where X belongs to this SN and A belongs to ON. And this is a matrix multiplication and the vector spaces are there. So this is really, this is clearly, this is actually clearly this is actually smooth group action, smooth action. Now I will use that theorem which I have really stated that. So I look at this this is I will use that theorem which I look at this thing ON dot Q naught. Now by the previous theorem, I look at this orbit of ON acting on Q naught. This is really WK. This is a actually, and this group is compact. ON is a compactor, so this is an embedded submanifold. Embedded submanifold of where? Manifold of SN. And WK is diffeomorphic, and WK is diffeomorphic to, this is the group by this stabilizer of this thing, and stabilizer is really OK cross ON minus K. So hence we get a smooth structure on WK, so that this OK cross OK cross N minus K is really diffeomorphic to WK, and this is really, this is WK is an embedded submanifold. Embedded submanifold of SN. So that means, so this and this OK, the smooth structure of OK mod OK cross and ON minus K, this is the same thing as really This is actually GKRN, right? So this is actually GKRN. Hence we get that GKRN diffeomorphic to WK is this. Hence we get the GKRN is an embedded submanifold of S. So therefore, thus GKRN is a Riemannian matrix. Manoj, is it clear?
Yeah, so I have a couple of questions. First, how are you determining the dimension of GKRN?
GWet dimension, I told you that dimension of GKRN.
Yes.
So this is dimension of ON minus. Okay, so let me write in
Oh,
the
you're
next way.
by that. Okay.
So I have shown that this is a Riemannian manifold, and I will show that this is a. Let us finish this small part. Actually, we will not be able. Just finish this. This is a Riemannian symmetric part. Okay, I will take 10-15 minutes. Okay, so let us finish this. Okay, so now our next goal is this GKRN is a Riemannian symmetric. Yes, I have to fix that. So I look at this example. The thing is, if you really do systematic way, then everything is clear. I hope everything is clear. So the example. So let us take this G1 of R2. G1 R2 is really RP1, and this is really S1. So this RP1 collection of lines in R2 is really you can identify it with S1. So let us see how this identification is done. So you really take this point Q, say this point Q. You just draw this line through this point Q. So this point Q will be represented by a line in G1 R2. Similarly, if you draw any line on this G1 R2 wherever it meets the circle, so this is point, this say X. So this line is really your the this is the line which will be represented by X. Okay, so for a moment, I will really think that points of circle are not nothing but this line on G1 R2. Okay, so this is really we are thinking that points of circle are line in G1 R2. So this is, so what is my SQX? Okay, sorry. So SQX is this line, right? So this is my SQX. Okay. So if you think about in the desk, so if you want to describe this SQS in terms of line, this is just reflection of, okay, so line X with respect to line Q. Now you want to generalize this idea to really higher dimension Grassmannian. So this is really SQ of T you want to define, where T, Q, T belongs to WK, Q and T are, this are really K planes. So this will be something like a reflection of K plane T with respect to this, the K plane Q. Okay. So this is my, this will work actually, this idea will work. So let us, but I have really defined in terms of K planes, but you will give this in terms of projection. So let us do that. So let RQ from to Rn to Rn be the linear map. Okay, so this is the linear map which takes this so that RQ is equal to identity on image of Q. Okay, so this RQ is equal to minus identity on image of Q per, right? So this What is the description for RQ? If you apply this on V, you take in V, this is really, you can write this is U plus U perf, where this U belongs to image of Q and U perf belongs to the really image of Q perf. And this is same thing as really U minus U perf by this description. So observe that RQ is RQ square is equal to identity. And this is RQ is an orthogonal mark. Okay. So therefore, and RQ square is the identity. So this means RQ is equal to really RQ inverse. And since RQ is an orthogonal market, RQ inverse is really RQ transpose. So RQ is a symmetric matrix. So okay, so let V be a subspace of Rn. What is RQV? So RQV is really RQV is the reflection of V with respect to the plane Q, K plane Q. The K plane, okay, let us write in the image of Q, because I am really writing in this projection thing. Q is a projection, okay, on image of thing. So now let us describe this thing, isometry in terms of the reflection. So SQT. Okay. So what is SQT? Let us write first this reflection of K plane T. So I am taking here as a plane T with respect to K plane Q. But I have to give this thing in terms of projection. So this is really projection. Okay, let us write this orthogonal projection. Orthogonal projection onto reflection of K plane image of T. So this is not T actually, image of T with respect to K plane image of Q. So this is really what? This is P of RQ image of T, because RQ image of T is really a reflection of the K plane image of T with respect to the K plane this image of Q. And this is really what I will use this relation P of AB is equal to A PB A transpose. This relation, if I will use this thing, RQP projection associated to image of T, and this is RQ transpose. Okay. Now projection associated to image of T, this is T, RQ transpose is RQ. So hence we get this SQ of P is equal to RQ T RQ, where Q and T belongs to WK. Now I have to really show.
Muna, I'm slightly lost. So in this step, so this why this projection with respect to image of T is equal to T? I'm just missing something.
Because okay, T is an orthogonal projection, right?
Yeah.
Okay, if you look at image of T.
So T
okay.
is any element in the capital T.
T is an element of WK. T is an orthogonal projection. T is equal to T transpose, and T square is equal to T, and this. Okay, and what? No, these two conditions. Okay. So what is the projection? If you look at the image of T, projection associated to the image of T, what? So you look at this map.
Orthogonal
You look at this
projection onto image of T.
GKRN and WK. Okay. So if you T here, what will go here? From WK to GKRN, when you go this side, you will get image of T, right?
Yes.
And here, if you look at something like image of T, if you look at the projection, how here, that will be your T, right? This is a simple
Yeah.
definition.
Yeah. Okay.
Yeah, it is better that you should really ask if there is some. Okay. So we get SQT is equal to RQT RQ. So okay. So yeah, okay. So we have to really show that this SQ is the geodesic inversion, and this is very easy in the sense. Okay, so okay, so you have to really show that first. SQ is an isometry, and this SQQ is equal to Q, and this SQ DSQQ is equal to really minus identity, right? You have to show that. So for that, what you do? Okay, two, you have to smooth. So SQ, observe SQ extends to a linear map. Linear map from Sn to Sn, given by this SQ of X is really RQ X RQ, right? X belongs to Sn. So this is a linear map. You can check that. So what is SQ square X? The SQ of SQX. This SQ is really RQ and SQX RQ. That so this is really RQ square RQ, RQ, and RQ square is identity. So this is really X. Hence, this SQ from hence SQ square is identity on this is really Sn, and SQ inverse. Therefore, this is really SQ. Now, since this SQ is a linear map, so since SQ is linear on Sn, since Sn is a vector space, also therefore SQ is really smooth on Sn. Now I am using this proposition now as Wk is an embedded submanifold. Submanifold of Sn, and SQWK is really contained inside Wk. Therefore, SQ from Wk to Wk is also smooth. Now its inverse is really itself. SQ inverse is also SQ. So since SQ inverse is equal to SQ, so this implies SQ is a diffeomorphism. Oh my God, I am taking a lot of time. So let us finish this. If I Pritam, do you have any problem if I will take 5 minutes more?
No.
Excuse a diffeomorphism from WK onto WK. Okay. So this is the thing. Okay. Now this is this diffeomorphism. We have to what I have to show that this is an isometry. So let U belongs to WK. So for isometry, so what I have to do? I have to show that G is the the Riemannian metric under WK. G of SQU. Okay, so let Y comma Z belongs to tangent space of DUWK. So G of SQU and D of SQ at the point U, Y, D SQ, U, Z. Okay. So this I have to really find. So now you use this fact that SQ is the linear map. So that is really SQ of Y. So this is really SQ of Z. I have told you that this is if something is a linear map, that derivative is okay as dsq of u is equal to sq. This is because of this fact that sq is a linear map. Derivative is itself, and this is by definition this is a trace of sqy and sq of z. So this is really what? It's trace of sq of y is rq, y rq, and sqz is rq, z rq. Okay, so this is really rq square is identity. So you use that fact that this is trace of this rq, y, z, and rq, but rq is really rq inverse. Okay, so rq square is I am using this fact rq square is equal to identity here. So this is really trace of yz because rq and this is same thing at g of u yz. So this fact is saying that g this sq is an isometry of this wk. So I am getting what I am getting. So hence I am getting. So we get this really sq star g is equal to g. Thus sq belongs to identity of wk, isometry of wk. Okay, so this is the thing. Now sq of q, I have to prove that two properties more. This sq of q is equal to q, and dsq of q is equal to dsq of q is equal to minus identity. This property I have not shown. So this is actually is easy because from this thing actually okay. So if you look at this description, so what is sqq? Sqq is the reflection of plane q, reflection of a plane q with respect to q, right? With respect to q, then you can really so reflection of plane q with respect to q. This is simply q, right? From geometrical description, it is clear. But some of you may not really like it. So what I do, I will do this thing really. So I will prove in a very rigorous way. Even to me, actually, that geometrical proof is also fine. But so what is sq q of v? This is really rq. Sorry, rq q rq of v by definition. And this rqqv I can write rqqrq. V you can write like this as u plus q per. This u belongs to really image of q, and this is really image of q. So now this is same thing as by definition rq of q. This is really u minus u per by definition of rq. Now u all belongs to really image of q. So and q is orthogonal projection. So q is equal to u. So this is rq of u. Okay, so let us write one step. Rq of qu because qu per this is rq of qu is u and rq of u is equal to u. Okay, and this is same thing as q of u plus u per, and this is same thing as q of v, and this is really happens for any v belongs to Rn. So that means this sq is equal to really q. Now, so I have to really, this is the first thing. So I am getting this sq q is equal to q. Now I have to really verify that dsq so is equal to really minus identity on claim. This is my claim on t q wk. Okay. For that I have to really know a little bit about wk. So tq wk is the claim. This is the thing actually I will prove to the next class tq wk. This is really x belongs to Sn, so that x of image of q is contained inside image of q per, and x of image of Q power. This is really continuous. So actually, I will continue in the next class. This thing, I will prove that only DSQQ is equal to minus identity, and this thing actually I will prove in the next class. Okay. So if there is any question, I will be happy to take it. So if there is no question, so I just okay. So
Can
you
stop the
can
record.
stop the recording. Is there any question?